sort of a building of theoretical ideas that appears to stand firm. And at any point, it could have gone completely wrong, and any little inconsistency will make everything crumble down.
Ivano, let me start with a simple question. What is string theory?
No idea. This is actually the answer that the experts will give you, right? But okay, it is a vast subject, of course. I can give you what I think it is, or at least what the hints so far indicate that it is. It's, to me, it's a theory. It's a physical theory, right, about all fundamental interactions, including gravity. It's a theory of of space, time, matter, interactions, all of it. But it's during its few decades of existence, people started answering this question a bit differently. They started saying, "Oh no, it's a toolbox to build theories," right? That's what some people would say, and in some sense, this is true. It's similar to frameworks of physics like Newtonian mechanics, which is like a toolbox to build mathematical models of physical systems, right? You specify, what stuff is, the kinematics. You specify what it does, the forces, the dynamics. And then the equations of this theoretical framework tell you what the system does. And we refine this idea further and further, going to all the way to, let's say, relativistic quantum field theory, and how it helps us understand particle physics, for example, cosmology, and so on. And string theory, in some sense, is a physical theoretical framework of this type, because it builds consistent models of gravity, quantum fields, and other things. But I would call it a physical theory rather than a toolbox, because all these various models that it builds are not separate. They're not like different universes or completely different theories. They are actually part of one whole set of physical laws. It's unique. The theory, as far as we understand, it's unique. It's a radical departure from even the cutting edge status of particle physics, where essentially you get to specify what kind of particles you have, what kind of interactions they share, with some reasonably rigid set of rules, but you have some freedom there. You can just specify, oh, I have a world in 7 dimensions with 16 types of electrons, or 4 dimensions and 5 types of electrons, or whatever. And these things do not talk to each other. At least most of the time they don't. They are unrelated theories of physical universes, well, imaginary universes, perhaps. Whereas in string theory, everything is connected. So you don't get to separate things, right? You can have different sectors of the theory, but the underlying physical laws, the rules of the game, and not only the rules of the game are the same, but the stuff that is there and how it interacts is the same. You don't get to choose. So to me, string theory is a physical theory. It's not just a toolbox to build models. It's one set of unified physical laws that hopefully can describe a universe, but even if it doesn't, it describes consistent universes according to all the rules of physics we know. So that's more or less my answer.
If I understand correctly, and please tell me if I'm wrong, we are talking about a physical theory in the same sense that, I don't know, quantum electrodynamics is a physical theory, or general relativity is a physical theory, regardless of whether they are consistent quantum and so on, right? But then we have this idea of building different models that are somehow related to one another.
Yes.
I guess our audience might be a bit puzzled here. where do we find these models? Where's the unique theory? Is it a matter of scale energy or something
It is.
else?
It is. It is indeed. So I think I can perhaps I can make an analogy with our most beloved physical theory of particles and interactions that we understand, which is the Standard Model, right? So the Standard Model is very well celebrated description of particle physics, but in the modern understanding of theoretical physics, it absolutely does include gravity and all other things. It is just it does so in an incomplete way. It's not a complete theory of all interactions, but it does include everything we know, except for a few holes like dark matter or strong CP problem and so on. But that aside, it does include gravity and particle physics and all their interactions. And this theory is it's a quantum mechanical theory of stuff, let's say particles, gravity, and other interactions. And as a quantum mechanical theory, it describes a physical system which has, states. Like a physical system can be in a state. And amongst all these states, there are special states which are sort of the ground states, what we call vacuum states in this context, which are essentially states of minimal energy in some sense, a sense which can be made precise because in gravity the story is a bit subtle, but it can be done. And the point is, you can ask how many such states there are. And already in this modern framework of Standard Model, thought of as an incomplete theory including gravity and particle physics, already here there are a gazillion different such vacuum states. And if you are an observer that only probes energy scales that are very, very close to this threshold, to this minimal threshold, you can approximate what you see with different physical theories, right? Which are approximate descriptions of the full story, right?
So when you're close, if I may, to a vacuum state, you actually probe an approximate theory. But
Yes.
here, I need to ask you something to make this very clear, because usually when we discuss vacuum states of the Standard Model, we typically fix stuff like the number of space-time dimensions by hand or the kind of particles we have. So those
That's
different states are
That's right.
kind of easy to
Yes.
imagine, because in the
That's
end you
right.
have photons, you have gluons, and so on and so forth. But in string theory, things seem to be a bit different or more complicated or simpler,
Simpler
if you
in
want
the
to flip the
yeah.
discussion. But please, can you tell us something more about this?
Yeah, that's right. So this is a very good point I wanted to get to. So some things are, fixed by the theory. Okay. For example, in the Standard Model, what you fix is the total number of space-time dimension. Let's say four. You can imagine a Standard Model in different dimensions, but let's say four. But this doesn't, because again, in the modern framework of physics, the Standard Model does include gravity in an incomplete fashion. You don't get to fix the number of space-time dimensions which are extended to infinity, right? You only get to choose the total in this field theory description, and therefore there can be different sectors of the space of possible states of the theory which have different numbers of extended space-time dimensions, right? So you can have sectors where all of them are extended, which is this particular simplest sector hosts the vacuum states that we usually describe in particle physics. But you can have different sectors where some of the dimensions are curled up, compactified or compacted as you prefer, and these different types of states contain different vacua, and these vacua are distinct, right? Now, so again, the analogy is meant to deliver this idea that the theory specifies some data. For instance, in this case, how many dimensions you have. But not everything. For instance, how many dimensions are extended. That is part of not of theory specification, but of the specification of boundary conditions or super selection sectors, or however you want to call it. But the point is that it's external input that the theory alone cannot possibly have. And we have many, many, many examples of this, right? Not just of dimensions, like, you mentioned quantum electrodynamics. In that theory, also the space of states is partitioned in sectors according to the total electric charge in the universe, and you cannot just expect the theory to tell you which one you're in, right? It's part of additional data that you need to specify. So in string theory, the type of data that the theory specifies seems to be exceptionally minimal, in the sense that basically it seems to be uniquely specified by very few consistency axioms, if you will. We don't have a full description of it, but whenever we have access to partial mathematical descriptions of the theory, it's always extremely minimal, in the sense that there's essentially no choice in specifying the theory. Now, there is choice in specifying the additional data, the additional data that describes what kind of states we're interested in within the theory. But we have much less choice in specifying the theory itself. For instance, again, we don't get to choose what kind of particles or degrees of freedom are present. We don't get to choose what kind of interactions there are. And we don't even get to choose the maximal space-time dimension, right? So there's that.
If I get your point, you're saying that whenever we work with a theory, there's something the theory kind of tells you, something else you can play with, right? And some additional conditions, like, boundary conditions. For instance, you mentioned the total charge of the universe. This is not something electromagnetism or quantum electrodynamics tells you. You have to put it in by hand and then study how such a universe can evolve and transform and so on and so
That's right.
forth. Yeah. In string theory, you somehow, whatever that is, I like the fact that you're trying to be kind of agnostic on the full theory, since we don't fully understand it. So I like this kind of conservative approach to it. But there's something we're kind of sure about, namely that the theory itself fixes a lot, right? You do not choose the particles, you do not choose the number of space-time dimensions, but you have some other sort of... Pardon
I
me?
would say I would say you don't get to choose the maximal number, but
The
you
maximal
can.
number of space-time dimensions, yes. Yes,
Right.
that's correct. But you have some other parameters you can play with, which are like boundary conditions for your states. So can we get a bit deeper into this before discussing how the states actually look and connect
Right.
to physics
Yeah.
we can observe?
Yes. Well, so again, so part of this, set of pool of choices can resemble the ones that I was describing earlier in the context of more familiar theories, like the modern description of the standard model. For example, again, you can imagine specifying how many space-time dimensions are extended, right? And then you can specify, for instance, the values of certain degrees of freedom at the boundary, at infinity, right? This is not news. We do it all the time in physics. We say, I don't know, I want to study electromagnetic fields in the presence of some conductor or whatever, and we say, at infinity I want my, energy distribution to die so that, the universe doesn't, collapse or whatever. So we do this all the time. It's not news. And in string theory, there are some such degrees of freedom whose conditions at infinity we need to specify. And so we can specify, again, the number of extended space-time dimensions, the type of boundary conditions that they have. For instance, they could be asymptotically flat, or they could be asymptotically, let's say, hyperbolic, or more precisely anti-de Sitter, stuff like that. And what kind of boundary conditions the various degrees of freedom have. For example, you can have an asymptotically flat space-time of dimension 7, I don't know, and then you have certain degrees of freedom which must vanish there because of the symmetries of flat space-time. But not everything need vanish at infinity. You can have scalar degrees of freedom, right, which can attain non-zero values at infinity without breaking any isometries, any symmetries. And so you get to specify these values. One example is the so-called string coupling constant. It's a number that tells us how strongly the degrees of freedom in the theory interact. And if this number is small, and again, this number is not a parameter of the theory, it's part of the choice of boundary conditions. But if this number is small, we can describe these degrees of freedom and their interactions in terms of strings wobbling around and colliding, and hence the name string theory, right? So in this description, we can talk about weakly interacting strings as a good description of the physics of the theory. And this is part of boundary data. Then, within such specification, so again, let's say however many extended dimensions at infinity, what kind of infinity they have, and what kind of boundary conditions for the various degrees of freedom there are. Within this sector of specification of boundary data, you can specify a state, right? And for instance, one way to specify a vacuum state, a minimal energy state, is specifying additional information which the theory must contain by consistency. For example, there could be additional curled up dimensions which are not extended to infinity, but there could also be something more abstract than that. This is why I was saying that the theory tells us that the maximal number of space-time dimensions is fixed, but it need not be the total, right? You can have less than that, but you need to compensate the extra, missing degrees of freedom with something else. And there is, again, in certain regimes of the theory, we have access to more or less precise definitions of what these things must be. And an example of that is additional curled up dimensions. And you can have, the total number can be as many as 10 if we want our description to be weakly interacting and stable. If we don't require stability, you can go all the way up to 26. And if you do require stability, but you do not require that the interactions be weak, you can go up to 11, in fact. So that's more or less the story. And these are, to me, they're maximal numbers. They're not the total number, right? There need not be exactly that many dimensions. There could be. At least the theory tells us that these are possible states. But the extra curled up dimensions may be, in fact, I would say that generically they are substituted by something more abstract. Additional degrees of freedom, let's say, that are encoded in how these strings interact and what kind of states they can be in. So maybe to summarize, because I said a lot of words, in string theory, you can specify some boundary data, including the number of extended space-time dimensions and the boundary values of different fields, the degrees of freedom, among which a number that tells us how strongly the strings interact. And then within this specification, you can further specify a state. In particular, vacuum states are reasonably well understood, and they need to specify, let's say, either additional curled up dimensions and their shapes and sizes, or something more abstract that replaces that. But the interactions cannot be, played with. You don't get to choose any of that.
So in a sense, consistency conditions kinda force you to do much more than they usually do, right? For
That's right. That's
instance,
right.
understand
Yeah,
that
yeah, yeah.
model. But here, there might be a point to make clearer, in the sense that from the perspective of someone who's heard of gravitational waves being observed by LIGO, or particles appearing in particle accelerators, or cosmology being such and such and so on, all this might sound a bit abstract in a way, right? So how does this discourse around boundary conditions and extended dimensions and string couplings then connect to the kind of phenomenology we typically talk about when
That's
coupling
right.
the standard
Yeah, yeah.
model of particle physics and general relativity, which is what you were discussing before, and so on?
This is a very good question. So, like, let's. I always like to go by analogies with stuff that is probably better understood, right? So, for instance, within the theoretical framework of the theory of relativistic quantum fields, how did we get to particle physics? We got there not merely by internal consistency, right? That leaves you with a reasonably large pool of possibilities. We got there by comparing with empirical observations, right? We got there because we discovered in a particularly long-winded road, in hindsight, that the types of particles and the types of interactions are described very well by such and such particular details, right? That the theoretical framework just doesn't tell you anything about. And similarly, in string theory, we don't get to choose these high level details. We don't get to change the theory, but we get to choose the low energy, physics around the little fluctuations around a given vacuum state, or something close to it, like a weakly curved cosmology or something like that, which is not a proper vacuum state, but it's close enough. I mean, the curvature is not that huge, and the expansion rate is not that huge. So what we get to choose is a vacuum state or something close to it, and then all the little ripples around this vacuum state are completely determined, right? What kind of we know again by general results in this vast theoretical framework, that because we have relativity, because we have quantum mechanics, whatever low energy physics describes these little ripples around the vacuum state, they will be described by a quantum field theory coupled to gravity. So it's a system that describes particles, or quantum fields if you want to be more precise, interacting between amongst themselves, including the gravitational field. And this will be described by a theory, by a model of this type. And so essentially we have a pool of such theories, of such apparently distinct theories, but we already know that these are just the little approximate ripples around states in the same underlying physical theory. That was my message from before. So we don't get to just make up particles and interactions to fit observation, right? Like we could do to some extent in the case of the standard model. But we get to search, we get to to sift through this pool of vacuum states, or approximate vacuum states, to look for something whose ripples around it, the kind of particles and interactions describe the physics that, compared to the natural thresholds of string theory, are low energy, even though for our current technology they are very much high energies. And we get to essentially look for something that looks like what we see. That's the idea of string phenomenology, if you will, trying to look for within this pool of options, trying to understand if there can be some of these options that describe low energy physics that look like what we see.
So, in a way, instead of adding particles by hand, we scan among the kind of vacua string theory offers
That's right.
and study small ripples around them, like because we are bound to stay at low energies with our experiments, right? Low energies meaning not high energy string theory
Yeah,
stuff.
that's right.
But here I have a question, namely, it's all a matter of variety and size of this space of vacua, right? Because if on the one hand they are not like chosen freely because they come from some deeper unique theory, apparently unique at least given what we know, which is
Yes.
string theory. If any theory can be found as a small ripple around the string theory vacuum, this is not much useful, right, for phenomenology, right? So my question, made a bit clearer, is the following. Can any kind of quantum field theory coupled to gravity in a given number of space-time dimensions, smaller than the maximal and so on and so forth, be obtained as ripples around a given string vacuum? And if so, is there any low energy predictive power at all?
Right. So this is a very very good question. Let me answer the last the last bit there. So let's suppose that indeed anything goes. Let's suppose that any such quantum field theory coupled to gravity appears as a low energy approximate description of some vacuum or approximate vacuum states in vacuum state in string theory. Then what then? Well, even in that case, I wouldn't be so pessimistic about the theory predicts nothing or whatever, because again, in the case of the standard model, we got to essentially build the theory according to what we saw, and if anything goes, it should mean that somewhere in there should be something that looks like the standard model, right? And then the question is a second order question of how many such theories look like the standard model, but then they differ somewhere else, and then we get to probe that. So the issue there, I would say, is not that if anything goes, then there is no predictive power whatsoever. Is that if anything goes, because it's very hard to find models that look like the precise standard model we see at low energies, then there is a problem with predictive power. But not merely because anything goes, but because anything goes and we cannot, pinpoint precisely something that looks like a standard model whose new physics predicted by the theory we could then test. So this is sort of the worst case scenario where anything goes, and we could also fail to find the proverbial needle in the haystack. Right? Now, luckily for us, the answer to the first bit of the question, does anything go, is no. It's not true that anything goes. In fact, I would be even bolder and I would say that almost nothing goes, in the sense that the pool of these quantum field theories coupled to gravity that emerge from low energy ripples around vacuum states, blah blah blah, in string theory, is in fact extremely small in a technical sense relative to everything you could just naively write down, without thinking about the internal consistency of the full theory, right? It's extremely small. It could be, it probably is huge in absolute terms, right? It could be, it looks like it's either finite but very big, or perhaps infinite but countable, right? Like how many natural numbers there are.
Okay, let me jump in here and then I'll allow you to proceed. But just to just to be clear, you're saying that given the set of all kinda plausible, in some sense, quantum field theories coupled to gravity, stuff your quantum field theory 2 professor would give you to study in an oral exam or a written one,
Yeah,
just a very tiny or even countable set comes from string theory.
that's right. That's right. So either I would say that the evidence points to the idea that it's either countable, that it is countable, period,
Mhm.
and that it could be even finite. right? Now, finite can still mean absolutely gigantic, right? It could be like 10 to the a number with 6 digits, or we don't really know. Like there are many estimates, but they are definitely very much rough and incomplete. So we don't really know. But any finite number, no matter how big it is, will never compare to the huge, uncountable infinity of such theories that you could naively write down. So the set of these options that the theory gives us is tiny in relative terms, even if it's huge in absolute terms. That's what I would say.
So, just to make a comparison, what about, for instance, a theory people might be more familiar with, which is general relativity? In general relativity, would you call different vacua, like states with different values of the cosmological constant?
No, I would call them, well, they are vacua in different theories, rather,
Yes.
I would say.
Okay. Okay. And so you told us that among all thinkable quantum field theories, plausibly finite, almost surely countable or surely countable set can come from string theory. How do you distinguish between them? Like, is there any tool to help you distinguish between theories that can actually come from string theory as low energy effective theories and others that can't?
So luckily the answer is yes, but the story is definitely far from complete, right? Like there is no full list, of tests you can perform that definitively tells you, unless of course you have a proper construction of such theory from the underlying string theory. And of course some of these checks involve a superficial application of basic consistency principles like unitarity, for instance, like the idea that the axioms of quantum mechanics should hold, and stuff like that, like the probabilities should sum to one and should be positive and all that stuff. But that this is superficial kind of it's a superficial criterion, right? That doesn't really directly involve the fact that these theories may or may not arise from string theory. So in the end, it does boil down to consistency principles, but it does so in a very subtle way that we could have not anticipated without looking at the deeper structure. So what we end up with is, at least for the scope of this particular question, with noticing patterns that the pool of theories that string theory provides at low energies exhibit. So there are some general features, right? General features that all these theories share. And some of these features we more or less noticed by just systematic scans, like you said, of these pool of options. At least the very tiny sub pool that we have access to, which is potentially very small, because again we are far from understanding the full theory, let alone its implications for this kind of things. But still, we have access to a sufficiently large pool of options that we can sort of notice patterns. And sometimes such general features go beyond just mere patterns that we observe. They can actually be proven to hold in general. In fact, some of my recent work goes in this direction. But works of this type go back to several decades ago, I would say. So there are certain features that we can actually prove hold, if not in the full string theory, at least in a large class of such vacua and quantum field theories that appear from them, and some other features appear so far as patterns that we see. that do not really have a deeper understanding behind them.
So in a way, these vacua, which seem to come from string theory, share features, right? Common
Yeah,
features we can just observe by looking at the theory, right? Stuff like, I imagine, stuff like symmetries or particle contents or stuff like that. But
that's right. That's right.
to make this a bit more concrete, can you make some examples of these criteria, right?
Yes.
That's the big thing here.
Yeah, yeah, yeah. So I think perhaps the conceptually simplest kind of answer I can give to begin with is that, what is essentially the coarsest data that you can glean from like such a quantum field theory. Essentially, how many particles you have, right? How many distinct types of things appear in the theory, and what kind of interactions they have. And these interactions are also described by mediating particles, and how many of these particles there are also informs what kind of interactions you have. The key word is gauge group, right? Like there are interactions mediated by gauge bosons, and how many gauge bosons there are is part of this specification of what kind of interactions you have. So one of the coarsest types of data that defines such a theory is how many distinct particles there are, or distinct types of quantum fields, more precisely. It turns out you cannot get however many you want, right? There seem to be sharp bounds. Essentially, what happens is that within any given class of string theory vacua that we can, classify well, there are sharp bounds on how much stuff you can have at low energies. You don't get to just put like 2 trillion types of particles and just call it a day, even if the theory by itself would naively look perfectly consistent. It turns out that string theory just doesn't produce that. It never produces hugely huge populations of different types of particles in the theory. And we don't have a complete deep understanding of this. We just know that in any given class restricted setting where we can answer the question, what is the maximal number of distinct types of particles we can have, the answer is always, so far at least, less than a number which is not particularly huge, like in the tens, I would say, or hundreds. Well, depending on the type of particle, of course. If we're talking about scalar fields, then there could be maybe a bit more than that, maybe in the thousands, I guess. But there are bounds, is what I'm trying to say. This is perhaps the simplest kind of thing. Then there are more subtle things, that are harder to definitively test just by looking at the low energy physics. Stuff like string theory has no global symmetries. It has no, conserved quantities beyond the ones that are super selected by, such as electric charge, for instance. It has no stuff like, well, the standard model has certain global symmetries that involve, for instance, conservation of certain combinations of the number of baryons and leptons and stuff like that. In string theory, this cannot happen. Right, there are no such conservations beyond the big ones like electric charge and stuff like that. The gauge redundancies.
Well, here I need to interrupt you, if I may, with a question,
Yeah,
just to discuss this explicitly, right? Because on the one hand, you tell me that the standard model has global symmetries of some sort, and on the other, you tell me that string theory allows for no global symmetry in its low energy
yeah,
vacua and so on and so
yeah.
forth. So how do these two things match, right, in a way? Or are we already sure the standard model cannot come from string theory from the fact that it has global symmetries, and then we just give up on it and move to something else? So what's the
Right.
catch here?
There is a catch, which is what I was trying to imply when I said that this is a more subtle criterion, right? So stuff like how many particles you have and what kind of interactions there are is easily, testable just by looking at the low energy physics. Stuff like there cannot be any global symmetries is not that easily testable because some symmetries may be only approximate, right? They may be approximate when the observer probes very, very low energy physics, but there can be effects coming from higher energy scales that in fact show you that the whatever conservation law you had is in fact absent or broken, right? Like for example, let's say a conservation law may tell you that if you take like an initial state with a certain value of some allegedly conserved quantity and you let it evolve in time, right, it will never reach a final state with a different value. That's what it means for a quantity to be conserved, and it's deeply connected but not exactly equivalent to having a global symmetry. And what could happen is that you experimentally measure that the probability of such process is less than 0.000000, and then you cannot resolve anything different from 0 within your experimental threshold because you're probing low energy physics. But the idea is that if you were able to probe higher energies and or more precisely what kind of process you're looking at, you would actually see that eventually this string of zeros ends in a 1 or in a non-zero number ultimately, signaling that the conservation law was actually never there, but it is approximately there at low energies, right? Or if you don't measure precisely enough. That's the idea. So this is why criteria of this type are subtle, because they can, even if the theory at face value looks like it can have a problem with such a criterion, ultimately something can come from higher energies and save the day, even if you don't know. And that's tough to test, in fact, right? You can usually give an estimate of the worst case scenario, right? Like how many zeros do I have to see before I see a 1? There is a way to estimate this kind of thing. But usually these worst case scenario estimates are essentially hopeless for any practical purpose. Like the number of zeros you would have to check before you see a 1 is just ridiculously big. It's not even worth talking about. It could be that we're lucky and then we see it earlier than that. But yeah, that's why it's a very subtle condition. But it is there nonetheless. It is a shared feature of string theory vacua.
And this is quite interesting because we've been discussing string theory in a specific sense. But you never know, some of these conditions might be more general, might be, tied to the fact that you need quantum gravity and not string theory in particular. So how's the state of that? Are these criteria expected to be there? Maybe not all of them, maybe some of them are specific to string theory, but maybe some of them might be, quantum gravitational in general. Do we know something about that?
Yeah, absolutely. And so this is like really the crux of the matter, I would say, because we can start going a bit in this direction by simply observing that at this stage there could be there is the logical possibility that there is like other despite string theory being a unique very rigid theory including quantum gravity, that there could be other such theories, and if so, would they share some of these features, right? We already know that because the standard model also has this multitude of different vacua, we know that any such theory will have multitude of vacua, right? It's just a general fact about quantum gravitational theories. But will these multitude of vacua share similar features, as you said? And the answer is yes. So that we have various independent motivations to think that at least some of these shared features are in fact just a consequence of these theories being quantum mechanical, containing gravity, and being consistent. That's and to be a bit more precise, by including gravity, what I mean is that the low energy physics contains general relativity as an approximation, right? It's not enough to just have something that looks like, you know, gravitons or something like that. Like, the interactions of these guys need to be described by something that looks like general relativity plus deviations from it. So this is what I mean by quantum gravity, right? A quantum mechanical theory that reduces to this kind of approximation. And it seems indeed that many of these features appear as consequences of this, or consequences of your starting theory, including gravity, being quantum mechanical, and being, consistent with the basic principles, unitarity, causality, and stuff like that.
Let me focus on a specific example, because a few answers ago you told me that the absence of global symmetries, the expected absence of global symmetries in a low energy theory, comes from the fact that string theory has no global symmetries, right? You phrased it like that. Is this a criterion that we expect to hold even in a more general quantum gravitational setting? Is this specifically string theoretic? And if so, can you provide me with some heuristic or, line of reasoning and hint at why it may hold just because of gravity and quantum mechanics?
Right, exactly. So indeed, in the context of the preceding discussion, we were just focusing on the consequences of string theory proper, you could say. Now, whether or not it is the only option, we can argue for some of these features, such as the absence of global symmetries, independently, right, of whether string theory is in fact the only option or not, right? That's the point. And we can argue for it based on, the consistency of quantum mechanics and gravity. And in particular, for the case of the absence of global symmetries, there are a number of independent arguments that sort of co-imply each other in a very neat way. And so there is a story there that seems to be very convincing, at least to me and many of my colleagues, that the absence of global symmetry is necessary for consistency. It's a necessary consequence of consistency. And again, because there are many options to argue for it, I have to choose one, at least to begin with. But rest assured that because there are many different ways to see this and they co-imply each other, the story behind this idea is reinforced, right? That's what I'm trying to say. It's not just heuristics. It's more than that. It's in a Bayesian sense, if you will, there is the co-implications of this network of ideas is much stronger than just a single heuristic. That being said, here's one. So usually many arguments, many thought experiments that conclude that a consistent theory of gravity must have certain features start with what is thought to be special about gravity, about a quantum mechanical theory of gravity. And one of the most special and unique things about quantum gravity is the presence of quantum black holes. Right? And black holes are very special in with respect to many other types of interactions and that are non-gravitational, many different types of objects, because their features are unique, right? They exhibit, big black holes have a huge entropy, for example, but it's not just huge; it's huge in a special way, right? It depends on how big the area of the event horizon is, and more than that, it's this feature holds. If you take a big black hole and its entropy scales like the area, approximately, if you make it bigger, the approximation will be better and better, right? This is in contrast to non-gravitational theories in which, in very special regimes, you can have certain objects certain solitons, if you want to hear the keyword, that do have such area-like dependence of the entropy, but only for very special points and special regimes. Whereas black holes have a continuous spectrum of options, of states that have this area scaling of the entropy. This was noticed in the 70s by Gibbons and Hawking, and this led actually to, well, I guess the idea that symmetries be absent in gravity goes back to 1957. It was discussed by Misner and Wheeler, so it's a very old idea that definitely predates string theory by decades. And it all goes back to, again, the properties of black holes. The properties of black holes include that they have a huge entropy, and that, except for special cases, they emit Hawking radiation, right? They evaporate very slowly. So these two properties are key to understand, why symmetries should be absent, at least from this point of view, but there are alternative points of view to see this. And one way to see it is that, if you take a huge black hole where, this approximate description of the large entropy and the, approximately thermal radiation is reliable, what you can do is you can start doing Gedanken experiments by throwing stuff in. And turns out that, if there were any conservation law involving matter, any type of matter, or more precisely for this argument, it needs to come from a continuous global symmetry, but these are details. If you throw stuff in, you make the black hole bigger. And remember that the bigger a black hole is, the better the approximation we're using is. So this is the idea. We're never actually going outside the regime of validity of the approximate semi-classical gravity kind of description. So you throw stuff in that had a conserved charge, and then the additional mass and size of the black hole can be evaporated away with radiation. But because in this regime the radiation is approximately thermal, it's like a black body essentially, there is a high chance, at least, that the black hole will not radiate away any of the conserved charge, right? So it's not like you throw stuff in and then you get back out the charge, and then at the end of the day, you started with 10 amounts of charge and you end up with 10. There is a very high chance. For the argument, all that matters is there is a non-zero chance that you end up with a different amount, right? And so you can say, oh, but then the charge that is missing is not actually missing, it's just inside of the black hole, right? It is just stuck there. Well, that would be okay, except that because black holes have a finite entropy, if this were true, you could just shove in enough charge and wait enough time to let the black hole go back to its original size, that the distinct states that you would need to resolve the different types of charge would vastly outnumber the total entropy of the black hole, and this is impossible, and it violates all the laws of thermodynamics and unitarity, everything. Okay, but then you could say, no, but wait, the charge is still conserved. It's just that it gets sort of stuck after the black hole becomes very small, and then you cannot trust your analysis anymore because the black hole is very small and the curvature is very high, and you don't really know what you're talking about. But actually, I can also avoid that because I can work with a situation. I can engineer my starting initial conditions and the amount of charge that I throw in the black hole in such a way that this situation can never be reached, no matter what the final detailed macroscopic physics is. I don't need to know. All I need to know is that in order to shed the charge, the black hole would need to be more massive than it is, and it's not, therefore it can't, no matter what the underlying physical laws that I don't know are. So the power of this argument is that it never gets out of the regime of validity of the approximations we make. And all that matters is there is some wiggle room for the conservation law to be broken. And then it means that it is broken. That's more or less the idea. So the long story short is you make a big black hole, you throw stuff in, you wait a little bit, and then either the charge is broken or you break thermodynamics. That's more or less the idea.
This is a strong argument that makes things a bit more, understandable or graspable somehow, from someone who comes from general relativity and quantum field theory. But moving a step back, and after this, I'll move to the more personal while not private questions, right? But before that, you introduced us to this kind of family of criteria, right? Perhaps looking a bit in the future, or without, making. I will not force you to make bets or strong claims you cannot back up, nothing like that. But are these criteria somehow unrelated to one another? They're just randomly popping up from string theory. Yeah, sure, they all come from string theory, but is there any chance we can give them a deeper meaning, connect them to one another, group them somehow? Is there anything like that?
Absolutely. And in fact, I think this is the deepest aspect of this research program, is to not only understand the deeper motivations behind these ideas in a way that doesn't explicitly hinge on string theory, but also to connect them I mentioned before that many of these criteria sort of co-imply each other, right? There is a network of relations between these ideas. And so I think an important and deep aspect of this research program is to connect these ideas, not just merely give a list. Right? I hope I never used the word list because it's very misleading, and it's definitely very far from what this is. It's a network. It's a web of ideas that are very much connected to each other, and they reinforce each other. Because you see, if you give some, let's say again, you look at some Gedanken experiment involving black holes, like I just did, and I conclude something, and then I do another Gedanken experiment involving black holes or something else, like I don't know, the fluctuations of the topology of space-time, something like that, and I conclude maybe the same thing. It's reinforcing this story, or maybe I conclude something else, and then that something else implies the thing that I was starting with. And it's a network of things essentially, and it's very compelling. It's a consistent, sort of a building of theoretical ideas that appears to stand firm, and at any point it could have gone completely wrong, and any little inconsistency would make everything crumble down. And the fact that this hasn't happened, to me, is very compelling, and it's a hint that we're going on the right in the right direction. And so yeah, many efforts are going in this direction of connecting these ideas, and I think that the future outlook of this research direction is to continue, of course, doing that, but in a way that tries to connect back to the string theoretic origin of some of these ideas, and essentially ask the inverse question of, let's say I have these consistency conditions, do they actually imply that quantum gravity has strings, right? So this is for me the most interesting aspect. Then of course there is the phenomenological aspects of, can we use these conditions to actually maybe say something about the new kinds of physics we could actually observe in the real world. Yeah.
And while for you, and I agree on that, this is the most interesting aspect, for me this is a perfect point to end our technical questions, and as I said, move to the more, thank you, right, and move to the more personal while not private ones. So first of all, how did you get into this? Like, why did you pick this topic? Well, broadly string theory, and then more specifically what you do.
Well, it's a tough question. I guess it goes back to my teenage years, where I was studying physics and mathematics and all that, and I got very quickly in the in the theoretical aspects. Like I realized very quickly that this is what I was mostly interested in. And for a long time, I was, I couldn't decide whether I should have studied mathematics or physics. In the end, I chose physics for various reasons, including the fact that the lore is that if you do highly theoretical physics, you get to study a bunch of math, but not vice versa. Um, and so I was studying this kind of stuff, and eventually I got more and more into the fundamentals, right? The deepest underlying principles. I was just following the reductionist rabbit hole essentially, and I ended up. I remember reading a book by Brian Greene, The Elegant Universe, and watching the documentary, which you can actually find on YouTube if you're savvy enough. And I just got I got fascinated by it, and I sort of decided that this is what I wanted to do. Then I ended up in a bit of a rut in the later university years, like toward the fourth year, more or less, in the sense that I got super interested in a lot of different things, like condensed matter physics, the quantum Hall effect, and anions and superconductors, and not so much particle physics. I should admit, I wasn't really ever much interested in that, but I was interested in a lot of different things, and quantum information theory, tensor networks, and I didn't really know what to do. And so I ended up starting the thesis in a thing that essentially I came up with this idea after reading a paper about applying quantum information theory in tensor networks and so on to quantum field theory, right? To study non-perturbative aspects of quantum field theory. And I ended up sort of changing topics after a few months because it wasn't really working well for various reasons, even though my advisor was, great. And I was at the time I was attending some lectures in let's say fields/gravity/strings by my future advisor Sagnotti, Professor Augusto Sagnotti in Scuola Normale, and he sort of saw that I was struggling with my choices of topics, and he pointed out that he thought he understood what I was going through, and he suggested that I start the final, the actual thesis with him, which is what I ended up doing. And in doing so, I eventually rediscovered, the love for fundamental theoretical physics, and in particular for string theory, that I had, many years prior in high school. So the full circle, is what happened. And then eventually, after starting my PhD, I discovered that I definitely, my worries were unfounded. Like I was worried that I would get trapped into doing maybe boring calculations and without much conceptual depth, or I wasn't gonna be free to explore the ideas that I wanted to explore. But all of that was completely unfounded, and I discovered that I absolutely had all the freedom to do all of that and then some. Right now my hands are way too full with lots of projects. But yeah, and then of course, after all of this, I inevitably butted heads with this research program we just outlined, the swampland program, if you will. And I started exploring it more deeply, and I tried to connect it with everything else, and try to find deeper motivations behind it and so on. And turns out that there are, oftentimes I explore some topic and it seems to me maybe it's not that deep conceptually. It's not particularly rich. It seems more like merely technical exercise and calculations. But this was different, right? There's some conceptual substance to it that the more I look into it, the more fascinating I find it. And so yeah, this is how I got here.
Thank you very much for the complete answer. And in that sense, do you have any, given your path in particular, right, going back and forth and not being sure about what to do next, do you have any suggestion for students who might be interested in getting into this kind of topic?
Yes. Yeah. So I definitely have two suggestions that I would give to my past self as a reassurance. One is, I think it's absolutely crucial. I cannot emphasize this enough to have good foundations, theoretical foundations at least. And by foundations, I mean, very as firm as possible a grasp on quantum mechanics, classical physics, thermodynamics, statistical physics, field theory, classical and quantum, relativity, general relativity, all of it, and of course the mathematics also, and so solid foundations are absolutely crucial. All of the well-established theoretical physics that goes all the way to the 70s or 80s, let's say, is like the most important thing, because so often, like, maybe students are pushed into pursuing extremely technical specialized topics, but then they have holes in even just conceptual holes in different areas, and they are unable, not by their own fault, or for lack of trying, but just by their background that they end up having, and they are unable to make connections between things, between ideas. They are unable perhaps to give deeper motivations for things by taking from different areas and putting things together in a way that is cohesive. Because the thing is, physics is cohesive. And as a dear friend of mine says, physics is one. Right? There is one physics, and so every time you study some topic, and you think you understand it, I think the most important thing is to connect it to everything else you know. Like, how does this make sense, right? You study the dynamics of fluids, classical dynamics of fluids, and you encounter the Navier-Stokes equations. Where do they come from? Like, is it just an empirical or semi-empirical model, or can you actually derive it from some more fundamental thing? And then you recall, oh look, I studied statistical physics. Can I derive it from there? And then you're like, no, wait, but this is equilibrium stuff, and fluids are not exactly there, but kind of. Can I do something there? And then you discover kinetic theory, and you connect the dots, right? And then you ask, oh wait, but relativistic quantum fields are just like anything else. Like, can I apply thermodynamics to quantum fields? And then you find out you can, and you discover all sorts of things, and your background gets more solid, broader, and deeper. And I think it's absolutely crucial. And this, gets to my second suggestion, which is, again, seeking these connections. Seeking connections and deeper motivations for stuff, right? Don't just stop at, someone important proposed this idea. Yeah, like, who cares, right? What's important to me is this idea, deep? Is it well motivated? Does it have important consequences? This is the kind of thing that I would focus on. Perhaps it's a bit risky to suggest, just going there, 100%, in the sense that focusing on deep, hard problems like these usually slows down publications, progress, and citations, and all of those metrics that usually boost people's careers. But then again, if you only do that just for the for the lulz, just to do calculations and put out papers without really any bigger goal in mind, what are we doing? That's the way I see it, at least. So these are the two suggestions I would give.
The way you see it's so important, and I want it to be so clear and to remain with our audience, that I guess that this is a right place to stop and thank you for your time and help, and I frankly hope to see you soon in Munich.
Absolutely, whenever you want. Always welcome.
Bye bye.